Good morning, everyone. We'll get started with today's class.
Good morning, sir.
Good morning, guys. So in the last class, we were looking at differential amplifiers. We started off with differential amplifiers. We were looking at what is called as a differential signal. If there are two arbitrary signals, we learned how to, form the common mode signal and also the differential signal, how to estimate the differential signal and the common mode signal. And we also looked at a very simple differential amplifier. And then basically we try to do the analysis of the differential mode analysis and also the common mode analysis. So we what is called as the differential mode half circuit and the common mode half circuit. And we also went through what is called as the differential mode gain and the common mode gain. And we defined those terms, what they were. We also defined the parameter CMRR, common mode rejection ratio. We looked at what it actually is. And then, we also derived an expression and we saw how the tail resistance is basically going to determine your CMRR. Now, if you recall in the last class, we were looking at a structure which was like this, right? You have two common source amplifiers, basically, but tied to a tail current source, right? So this was your V in P, this was V in M. Let's call this as RD or something like that. Now this was V out P and this was V out M. Now the same thing, the equivalent version can also be done using a PMOS transistor, right? So in this case, what happens is that you have a tail current source. In this case, happens to be a PMOS transistor, let's say, which is biased using a current mirror. And then you have a PMOS input pair, right? And you have resistors to ground. And let's say this is V in P and this is V in M. Now this becomes V out M and this is V out P. Right. Now, of course, here you have the NMOS tail current source. Now this obviously there is going to be some R tail which is going to give you the which is going to give rise to a finite CMRR. Okay. Now, how does this is the we looked at the small signal analysis. We looked at the small signal differential gain, the small signal common mode gain, but just and we also looked at what is called as the input common mode range, right? Which is basically this V in P and V in M can be written as V in P is VCM plus, let's say, VDM by 2, and V in M can be written as VCM minus VDM by 2, right? And in other words, this can be taken as VDM is nothing but V in P minus V in M, and VCM is nothing but V in P plus V in M divided by 2, right? So this is how we have also derived, or rather understood or decomposed these signals, right? Now what happens when, so we looked at the bias voltages, this common mode voltage, the DC voltage on which the small signal is going to ride. We saw what is the range, we looked at it, we also looked at the output voltage swing and so on. Now, what happens when you have a large signal behavior, right? So for example, let us take on the x-axis, let us take Vp minus Vm, or rather, to be consistent with what we have been seeing, let us take V in P minus V in M, and let the this be the output. Okay. Now, when you have both V in P and V in M, right? Both of them meet at this particular point, which is basically nothing but, let's say, this x-axis point is nothing but VDD minus I tail by 2 into RD, right? This is the x-axis y-axis point here, right? Now, as you increase the differential voltage, now what happens? Let's say this black one is the V out P. Now there is going to be a linear increase in V out P, right? And there is going to be a linear decrease in, let's say, V out M. Correct? Now, the vice versa is also true, which means that as the differential voltage V in P minus V in M goes below zero, the V out M starts increasing and the V out P starts decreasing. Okay. So you have linear behavior in this region where the differential voltage is quite small. The small signal assumptions do hold good. Now let us take the other extreme, which is, let us say, V in P minus V in M is a very large value. Okay. That is, let's say the differential voltage is now some 500 millivolt or 600 millivolt or 800 millivolt. Now what will happen to the output voltage? V out P, what will happen? Let us say, let us just take, for example, VCM is some 0.6 volt, and let us say the delta V is, we are sweeping from, 0.001 to, let us say, some 1 volt, right? So for very small delta V's, right, you are going to have a linear response. Now, let's say the delta V itself is some 0.6 volt. There is a supply voltage of, let's say, 1.8 volt or 1.2 volt. What will be V out P? So, which means that V in P will now become, okay, let me write it in the other slide. Okay. So, let us say VCM to be 0.6 volt. Let's say delta V to be 0.5 volt, which means that V in P is given by VCM minus plus delta V by 2. V in M is given by VCM minus delta V by 2, which becomes what? 0.6 plus 0.25, 0.825. And this becomes 0.6 minus 0.25, which is 0.3. Sorry, I think this is 0.85. Yeah. Yeah, this is 0.85 and this is 0.35. Correct. Now, if you have, let's say, V in P equal to 0.85 and V in M equal to 0.35, now let us say your nominal threshold voltage is around, let's say, 400 millivolt. Okay. What do you think will happen to V out P? So if you annotate it here, this is 0.85 and this is 0.35. What will happen to these two transistors M1 and M2?
Both have different current flowing through them.
Both have very different currents flowing. And mostly what will happen? The entire I tail will flow through M1. Right?
Yes,
And
yes, sir.
in fact, the M2 will almost turn off. Okay. In this example, I have given the threshold voltage to be around 400 millivolt. It is now in the subthreshold conduction region, which basically means that you might just have some, some hundreds of nanoamps or tens or hundreds of nanoamps flowing through because it is now in the subthreshold region, whereas M1 is in very strong inversion region, probably limited only by velocity saturation, and it is very likely to have the entire I tail flowing like this, right? Now, if your entire I tail is flowing like this, and let us say here in M2 there is literally no current, then your output is going to be what? V out P, which is the positive, which is this particular thing. This will go, what will be the value of V out P? Assume that the current through M2 is 0.
VDD.
It will be VD. So for very large differential voltages, it's going to be constant at VDD, right? Now, what about the other side? So let us say this is VDD. Now, at the same time, when your input differential is very large, what will happen to the V out M?
Close to zero.
You have a large amount of current flowing through. So
Close to
basically, it is going to go to a very small value, right? This is going to be a very small value. Hopefully, it is able to maintain at least the current source in saturation. Okay. So in between what happens, there is kind of a transition region like this. Okay. Similarly, you can say that there is going to be on the other side also, you're going to have something like this, right? When the input differential is the other way around, you're basically going to have a behavior which is very similar. So you have a linear region, and as you keep increasing your signal amplitude or the differential signal amplitude in this particular case, what you're going to see is that there is going to be a deviation from the linear behavior, right? And it is going to saturate at the higher end at around VDD, and at the lower end it will go to some very small voltage, such that maybe the current source itself sometimes can get M1 can go out of saturation, and only the tail current source might be in saturation. And it depends on what is the sizing, how the transistor behaves, and so on. All right. Okay. Now this is what is called as the large signal behavior of a differential pair. Right. Now, in the previous class, we kind of came up with the differential mode gain. What is the differential mode gain of this particular circuit?
GMRD by 1 plus GMRT.
No, differential mode gain. So if you take this, okay, just to refresh your memory, if you take the circuit, this particular point, let's call it point P, is a virtual ground. It's a virtual AC ground, right? So the differential mode half circuit turns out to be what? DM half
GM.
circuit. Yeah. The differential mode half circuit is basically this. You have VDD, you have RD, you have one of the transistors, and this is basically node P, which is a virtual AC ground, right? So the differential mode gain we found was minus GM RD. Now, if I want to increase the gain, there are two things that I can do, right? Because it's a product of two terms. So I can either increase GM. Okay, so option one is increase GM, and option two is increase RD, right? Now, how can you increase GM? We know the GM expressions. Either you can increase. So here, what happens is there is an input common mode voltage which is coming. So, and you are also fixing the current, right, through the tail current source, right? So, if you want to increase the GM, you can increase it by either increasing W by L ratio, right? Now, by increasing the W by L ratio for the same current, what happens? GM is given by 2ID mu n C ox W over L, right? So you increase the W by L ratio for the same amount of current, the GM is going to increase in proportion to root of W by L, right? Now, the problem is that as you keep increasing the W by L ratios, the device dimensions become very large, right? You end up with more parasitic capacitance. And also the GM is going to increase only by root of W by L, okay, which is not a very good thing, right? Now, the other way is basically to increase current, right? Now, increasing current basically obviously means that you are going to increase the power dissipation. Now, let us say that we are still within the power budget limits. Now, what this is going to cause is, one is of course power, and the second is basically that your V out CM common mode is going to drop down, right? Because as ID increases, the V out common mode, which is given by VDD minus ID times RD, this number is going to start going down. Now, as this number goes down, you have lesser amount of voltage left for both your M1 and let's call it as M tail, right? Now, this is going to do what? This is going to crunch your signal swing. So how is it going to crunch your signal swing? Let us say this is your VDD. Let's say this is your ground, right? First and foremost, you need, let us say, let's take this is 1.8 volt. This is 0 volt. Let us say you need some, at least some 250 millivolt to operate your current source. Okay. Let's say this is your VD sat plus margin for MT. Okay. So always in industry, when you design, you will never design, you will have a certain VD sat. Let us say, for example, the VD sat of the tail transistor is, let us say, 150 millivolt. Okay. You always try to have some 100 millivolt to 100 to 150 millivolt margin, so that your your tail transistor across PVT variation, as temperature changes, your process corner changes, or your voltage changes, and so on, you still have some room for this transistor to be in saturation. Okay, nobody puts it at the edge of saturation. So, for example, if the VD sat is 150 millivolt, you kind of give a 100 millivolt margin, and you take 250 millivolt to be the voltage to be there across your tail current source. Now, after that, what happens? Your this also has to have a, what is this? Let's say there's another 200 millivolt or 250 millivolt. Okay, across your M1. So totally at this point, now we are having 500 millivolt. So this is 250. This is another 250, right? So this is basically the VD sat plus margin for M1 or M2, correct? If you look at this particular circuit, right? So this output node voltage, right, now has only this much room to swing, which is, this whole thing is how much? 1.8 minus 1.5, which is 1.3 volt, right? Now this output common mode voltage, let us say VDD is this one. So let us say if you are going to, now where should you put your output common mode voltage? It should be in the middle of this 1.3 volt, which basically means that 1.8 minus 0.65, what do you get? You get 1.15, correct? 1.7, sorry, yeah, 1.2, and yeah, this is what you would get, right? So let us say if you put this DC common mode voltage at 1.15 volt, then your signal can kind of swing, let's say almost close to VDD and almost down here, right? This is where you will have the maximum swing for your differential amplifier here, right? Let's say this is your V out common mode, and this is your signal swing that can happen. The total signal swing is going to be 2 times this value. Okay. Now, suppose I'm going to say, okay, for some reason, I'm just going to just increase my ID, keeping the same RD. Now, what will happen? This will shift to, let's say, some voltage like this. Now, what happens? Here you have a larger headroom. You can go all the way till here, but here you're going to do what? Now you're kind of going to push these transistors into triode region. So you have some margin built in, but then what happens is, as you kind of some crunching starts happening, some non-linearity starts happening, and you start seeing some distortion. Got it? So basically your signal swing is kind of limited to only this much. If you want no distortion. All right. So what we are seeing here is that as you either increase ID, okay, or you increase RD, right? This is going to move your, it's going to restrict the max possible signal swing. All right. In other words, it's going to have an early onset of non-linearity. Okay. So what can be done? So this is kind of your kind of cut. You can, and already we saw about this GM by ID thing, and then you know that you cannot increase things beyond a certain limit. So what you need is that you need a higher load resistance while taking a lesser amount of, while dropping very less amount of voltage. So the solution to this problem is basically to say, okay, instead of a resistive load, I'm basically going to put a current source load. Okay. So conceptually, the differential amplifier now becomes like this. Okay. You have I tail here. This is I tail divided by 2 current source. I tail divided by 2 current source. Right. So let's say this is V in P. This is V in M. Let's say this is V out M and this is V out P. Right. Now, if you take the differential half circuit, how it is, differential mode half circuit, this is basically a current source with only this one. And this gain ADM is nothing but what? GM times R01. GM1 into R01. Correct. Now, we have already studied how to implement these current sources, how to implement the current sources, how to bias the current sources. Basically, you just put a transistor biased in saturation using current mirrors, you bias them up. So this circuit actual realization now is going to become like what? You have PMOS current sources. Let's say this is biased through some current mirror. Okay, we'll not worry about the biasing right now because we know how to bias it. In practice, actually, it is biased slightly differently, but we will look at it later. Okay, so let me just say, this whole part is not there. This is biased somehow, and then let's say this is your tail transistor. Let's call it as M0, M1, M2, M3, and M4. All right. Now this becomes V in P. This is V in M, and this is your V out P. This is your V out M. All right. Now this circuit, what is the advantage here? You've replaced the resistor using a current source, and that current source is implemented using a PMOS transistor. And the advantage of this PMOS transistor is that what is the voltage that it needs across the PMOS transistor? What is the voltage that is needed?
VD sat.
The VD sat. Right? It just needs VD sat across it to make sure it is in saturation. So, so even if you increase the amount of current, you are really not going to increase the VD sat so much, right? And what is the resistance that you get? You get R0 as your resistance looking up, right? So the differential mode half circuit is going to look like what? It's going to look like this. This is some VB. This is your differential mode half circuit. Now, can you tell me what is the differential mode gain? Let's call this as M1, and I think M1 and M4 were there. So let us take something. What is the differential mode gain?
GM into R01 parallel to R04.
Correct, right? So this one, it is a common source. Basically, what I have drawn here, the differential mode half circuit is nothing but a common source with a current source load, right? Which we have already seen. And the gain is given by GM1. This is your input transistor, the transconductance of your input transistor, multiplied by the total output impedance. Output impedance is what? Looking down, you have R01. Looking up, you have R04. So it becomes R01 parallel to R04. This is, of course, also equal to GM2 multiplied by R02 parallel to R03. Okay. Because all the transistors are supposed to be identical. Right. All the transistors meaning both the PMOSs are identical, both the NMOSs are identical. Right. All right. Now, what is the output impedance we have seen here? The output impedance, as we estimated, will be R01 parallel to R04, which is also equal to R02 parallel to R03, right? if there is a output capacitance, let's say is CL, now what is be your bandwidth of the system?
1 by 2 pi CL R naught 1
1 by
parallel
2 pi into CL into
CL
R02 parallel to R03,
3.
right? We have already seen how to analyze the noise of this particular amplifier. All the other things have been taken care of, right? And the common mode half circuit is going to be what? The common mode half circuit is basically going to be the very similar in the sense that you have VB here, you have Vin here, and you have what? R0 0 here, right? Yeah, V out. And the common mode gain is basically given by GM1 times R01 parallel to R04 divided by 1 plus 2 times GM1 into R00, right? Earlier we had 1 plus 2 times GR tail, 2 times GMR, sorry, this is going to be 2 times R00 because this transistor basically has R00, and when you it decomposes kind of when you form the common mode half circuit, it becomes twice the resistance, right? And this is what basically you will get, and therefore the CMRR is basically given by 1 plus 2 times GM1 times R00, right? This is your CMRR. All right. Now the other things we have already seen, and we have all I mean how it happens and so on. Now this transistor, this yeah, somebody had a question.
Yes, sir. Like earlier case also we are having the same CMRR. Now also we are
Right.
having the same CRR. So
Yes.
how does it make a difference if we want to increase ADM or if we keep it same?
Now, okay, a CMRR doesn't change, but then you're getting a larger differential mode gain, no?
Yes, sir. Like mostly we need a high CMRR instead of a high differential gain, I think. Like if you want the practical
Uh,
application of CMRR is useful.
yeah, so typically what happens is in typical CMOS op amps, you get a CMRR of at least above, 60 dB or so easily. Above 50, 60 dB, you'll easily get. Not only
Like
is the
what?
CMRR alone important, differential mode gain is also actually quite important, right? If you take an op amp, the assumption is that you have a very large differential mode gain, right? That is what makes it an ideal op amp. And so getting gain in CMOS op amps is a little difficult. Okay? So we will see that. Okay. So the advantage here is that without shifting your output point. So here the thing is you cannot. It is the output common mode voltage is not very easily. I mean, you cannot directly say, okay, this is going to be my output common mode voltage because it's a high impedance node, right? The VDSs can take any values, and only a simulator can predict what exactly would be the output common mode voltage. So we will come to that issue little later. We will once we go through the other things. Okay. All right. So this particular structure, what I have drawn, is what is called as a very simple 5 transistor. It's a 5 transistor OTA. Now, what is an OTA? OTA is nothing but an operational transconductance amplifier. Now, why is it called as an operational transconductance amplifier and not an operational amplifier? The reason being that the output impedance is quite large, right? So as we know that the output point is a high impedance point, the output impedance is quite large, and therefore it is best denoted as a transconductance amplifier, right? Some GM times V in with a certain R out, okay? With where this is your V in. Now, this usually, I mean, in the field of analog VLSI design, many times you just go ahead and call this as your op amp. Okay. So this 5 transistor OTA is also very commonly called as the op amp. But in a more stricter sense of the term, All that is stopping this from becoming an op-amp is that it doesn't have a low output impedance. Okay. Now, what do you think can be done to make this as a proper op-amp?
So we can use emitter follower thing.
Okay, so emitter follower in the case of BJTs, and here you have source followers.
Yes,
right?
yes.
So basically, you take this and you put it through a source follower. Okay. Now this whole thing becomes an op-amp. All right, and this alone is basically an OTA. Now you require a source follower when you are, you require a full-fledged op-amp, that is an OTA plus a source follower, or in general, it is called as you have an OTA followed by a buffer or a driver, buffer, whatever name you call it. This whole thing becomes an op-amp, right? Because anyway, source follower has a gain of almost 1, slightly less than 1, and it also gives you a very low output impedance. Now this is required. So in many of our analog VLSI or mixed signal chips and analog ICs, most of the time you are not driving any resistive loads. Okay, that is thanks to the way in which the MOSFET device is there. That is, at low frequencies, the input impedance of any transistor is only capacitive. Right? You do not have a resistive component at low frequencies. Right? At normal analog frequencies or mixed signal frequencies, the input impedance seen by any or offered by any transistor is only capacitive. So in order to drive capacitive loads, you don't require a driver or a buffer. Okay. And OTA can easily drive a capacitive load because you don't have to drive DC currents, right? You only need to drive AC currents, and capacitive load can always be driven by OTAs. Okay. So in many cases, we just use this as, in many times loosely, we call this 5 transistor thing as the op-amp. All right. And we use it only in cases where resistive loads need to be driven. You need to have your source follower or a driver or a buffer stage. Okay. All right. So this is a very simple op-amp, and this is what is called as a fully differential. This is what is called as a fully differential op-amp. Fully differential operational amplifier, or let's just call it as a fully differential OTA. Okay. And the way we usually use this is like you say, okay, now you have plus and minus terminals, and you have output also minus and plus terminals. Okay. This is what is called as a fully differential op-amp, OTA. Now we will come back to it and look at certain other issues, but I will kind of reserve it for one of the later classes where we look at how to do this biasing and so on. Normally, when you are doing biasing, you can just use a current mirror, but in practice, you cannot directly use. There is some arrangement called as a common mode feedback. We will look at it probably maybe a few weeks later. All right. Now, before I move on to a single op-amp, let me just give a couple of points. One point is that if you look at the CMRR, right, this M0 transistor, how will we size it typically? The sizing will be such that you increase your channel length also, right? Why will you increase the channel length of M0?
So that the channel length modulation effect is less, and also that whenever we have some extension of that gate, that will not affect the channel length. That delta L by L will be less.
RTL is more stable.
Correct. Okay. So all these answers are basically tied into each other. If you increase the L0, your R00 increases, right? Basically, it means that your channel length modulation is less, and therefore your R0 is higher, or rather this current source is more stiff, right? The gate extension and other things, okay, that is to say, I mean, that is not the reason why we have a larger length. The gate extension problem is solved by having identical lengths for all the current mirrors. Okay, and also another thing is that you have, you know, a current mirror sitting here, and then, you know, you want to make sure that the current is faithfully copied. Mismatch between these two transistors is eliminated. So all these other benefits are basically there, right? You also have a common mode flicker. This M0 will also have flicker noise. As you increase the area, the flicker noise will be lesser, and that flicker noise will be common mode for both of them. So we really don't care so much about it. Okay, so for all these reasons, mainly because to increase your CMRR, you increase your R00, right? And you increase their channel length. Now, what is the side effect of increasing area? Because if you increase L, you have to increase your W also correspondingly. What is the side effect?
Capacitance increase.
Capacitance, right? There is going to be a capacitance here, which is the CDB, the drain to bulk capacitance of 0, right? And of course, you'll also have the CSB1 plus CSB2 and all these things. Okay. Now, in fact, you want M1 and M2 to be matched to each other, and therefore to decrease the amount of random mismatch, you'll go and increase the sizes of both M1 and M2. So again, that will increase your CSB1, CSB2, and so on. In effect, let us say there is a capacitance CP. Now, what will happen? What will be the effect of CP at higher frequencies? Which parameter of the op amp do you think it is going to affect at high frequencies? Slew rate.
Bandwidth, sir.
Bandwidth.
Not necessarily. Slew rate will be affected if your output capacitance is higher. Okay.
Increase, yes.
Gain, sir.
Which gain? Differential mode gain or common mode gain?
Differential, sir.
I think CMRR.
Correct, CMRR, right? Why will differential mode gain be affected? Because this node P is already common mode, right? It's already a virtual ground, right? It's already a small signal virtual, it's an AC ground. Now, all what you're doing is, as at higher frequencies, it is becoming more and more not just a virtual ground, it is becoming an actual ground, right? So the differential mode gain literally does not get any effect because this node is becoming even a better ground, right? But what will be affected is basically the common mode gain, because now you're having a capacitance at this node, right? So if you have CP, you will have basically CP by 2 in your half circuit, right? And now what will this become? It will become 1 plus GM1 times 2 times R0 in parallel with CP by 2. Okay. So, or rather, this will be 1 by, or rather 2 by SCP. Correct. This will be the actual expression. So, what happens is at higher frequencies, CP results in CMRR decreasing due to the common mode gain decreasing. All right, is it clear? Okay, so this is why if you look at even any op-amp data sheet, even a commercially available op-amp data sheet, you will see that the CMRR, they would have plotted it across frequency, and you'll see that the CMRR is some really nice value at lower frequencies, and then it will kind of have a low pass behavior. Okay, why is that low pass behavior happening? Because of basically this. All right. Okay.
Sir, ACM increase.
Now, sorry.
Sir, ACM increase, I think. CMRR decrease.
Yeah. Sorry. Yeah, ACM increases and therefore CMRR decreases. Yeah, you're right. Thank you. Yeah, your common mode gain increases and your CMRR basically starts decreasing. Now this is one thing, and of course you can also have other kinds of variants on this. Sometimes people might go and put some, you know, I mean, you can have some, you know, degeneration here in order to linearize and all those kinds of things. Whatever you have, that is fine. But basically, you know, putting this resistor here will basically cause it to have some degeneration. So that will reduce your differential mode gain, but it will improve your linearity and so on. So those things are all routinely done as and when needed. Okay. So this is what is called as a differential OTA. Now, the question that many of you might be having is, what about a single-ended OTA?
Sir, one question before. How is a source follower designed for this if we want to design one? Will it also be a differential system?
Okay, the source follower will look something. It will not be a differential one. It will be a single-ended one only. Okay, but it will have, you'll have two single-ended ones. Okay, so
Got it,
let
sir.
me. Right. In fact, there is an the way you do it. There is a small trick which is there. Let's say this is your main 5 transistor OTA. Now this is your output. Let's say this is V out P, right? Let's call it V out P dash because it needs to go through a source follower. Now this voltage is actually little on the higher side. It will be like how we saw earlier. This voltage is going to be greater than VDD by 2, right? So yeah, so in this case, what you will do is you put up NMOS source follower, and you have a current source here. This is going to be your V out P. For V out M, it's going to become something like this. Okay, so let's say this is your V out M. Now let's put some names here. Let's say this is M0, M1, M2, M3 and M4. Let's call this M5 and M6 and M7 and M8. Right? Now here M0, M7, M8 are all current sources, right? These are all current sources. So they all can be biased using same current mirror. So typically what will happen is that you will have some current mirror here. Okay. And so in this particular case, you have so many transistors. So you have 4 transistors. Let's call this as M9. All right. So you have M9, M7, M0, and M8. All these 4 transistors are basically are forming a current mirror system. So in practice, in industry especially, or even when you're doing your things in project and so on, when you're doing layout, what happens is that this all the 4 transistors will be laid out together. Okay. So these 4 transistors together will form one common centroid layout, and then you will route it to all the other transistors. Okay. So it is not that although this M8 and M7 form a part of the source follower and so on, the layout will be done together, and it will be some, you know, kind of a common centroid layout. So maybe M9 will be in the center, and then you have all these things oriented in such a way that there is common centroid layout, and from there it will go to all the other transistors. Okay.
Sir, what M3 and M4 be also connected? Like ITEL by 2, that's why. Double weight.
Okay, so this, okay, so right now I will not go into it, but there is a slightly different way in which we bias it. So for example, let's say if this is also biased using another thing, so all the PMOSs together will be one current mirror, all the NMOSs together will be another current mirror. Okay, so typically when you have a 2-stage OTA with all those things, you'll have one bunch of PMOSs which are current sources and current mirrors, and you have one bunch of NMOSs like this which are current mirrors. So the PMOSs will be laid out together, the NMOSs will be laid out together. Okay.
Okay, sir.
Okay, sir.
Right. All right. So now this is how your basically your this will be. So the differential thing happens only for the first stage, and the second stage is all 2 times single-ended version. So this is nothing but a single-ended source follower which you use on both sides. All right. Okay. All right. So maybe with this I will conclude my class, and we will look at mismatch and also single-ended OTA and other things in the subsequent classes. All right. Now I'm just wondering, can we have one extra class maybe either this Thursday or Friday? Because last Thursday and Friday both days we could not have classes due to the holidays. Tomorrow maybe 3 p.m. or 3:30, can we have a class?
Sir, actually, we are having class tomorrow till 4 p.m., sir.
Till 4 p.m. Okay. What about Friday?
Sir, we can try for Friday, sir. I will inform you means on Thursday whether we can have class on Friday or not.
Yeah, maybe Friday around 3 p.m. should be good. So just
Yes,
let
sir.
me know.
Yes,
Okay.
sir. I will inform you. Yes, sir.
Yeah, MTech students, you guys are free that time, or do you have any class?
Yes, sir, we are free.
You're free. Okay. So Kshitij, you can just let me know Friday, or we can have a class at Friday 3 p.m. Okay. All right.
Okay,
So
sir.
thanks everyone. Have a nice day. Thank you.
Thank you, sir.
Thank you, sir.